All right, we're back. As we continue our unit on transformations in the plane, we'll focus on one of those rigid transformations, those congruence transformations that we talked about last time, the translations. There's a famous artist by the name of M.C. Escher who likes to do what's known as tessellations, but he uses translations, as you can see in these white birds and the blue birds, just translating the figure over in the picture to give the effect to get all those birds to fit together. Anyway, we'll talk about that more in detail as we go through our unit. So as we learned last time, translations occur in the same direction. So each point moves in the same direction, the same distance. So whether it's a circle or any set of line segments, they all move. This one moves to the left, same direction, same distance. This one moves down to the right. Okay, things maintain their congruence. These are not translations because even though they maintain congruence, not all points move the same distance. Okay, so how do we describe translations? So as we're going from the original to the image, notice the arrows show which way we're moving. So this one over here is the original, going to the image. How do we describe that in words? Well, we say it's translating. Okay, so it's a translation, and how do we describe it? Well, which way is it going? Well, it's going to the right. Can we describe it any further? Well, it goes to the right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units, and up 1, 2, 3, 4. So right 10 units, up 4 units. Okay, so we can use coordinate notation, just like we did learned a little bit last time, but to describe this one, we're describing how did the coordinates change. So the original, we're saying those are x and y. Okay, so now our new coordinate, well, what did we do to the x? Well, we went right 10 units. In that case, we're adding 10 to our x coordinate, and our y coordinate went up 4, so we're adding 4. And notice we can compare from this point, -6 plus 10 is 4, 6 plus 4 is 10. And if we were going to write this in the proper way, we'd say, well, x, y, and the image is x plus 10, y plus 4. Okay, so that would be the coordinate notation that we would use. Another example, how do we describe this one? Well, this figure, notice there's no arrow to indicate which way it's going, but the image is dashed. So typically the image will be a dashed figure. We can see that it's going down and to the right. So translation. We're going down how many units? From -6 down to -8 is down 2 units. And we're going right. Our x-coordinate goes from -3 to 5. That's right, 8 units. So original x, y are new. The x-coordinate goes right, left, so we went right 8. So we're adding 8 units. -3 plus 8 is 5. We went down 2 units, affecting our y-coordinate. So our y goes down 2. Okay? So that's the new coordinate notation we would use. So the next we can take a look at is this quadrilateral ABCD, and we can do the same thing. We can graph it according to the rule that we have there. And we'll graph using prime notation. We'll talk about what prime notation is. So go ahead and graph those vertices, and then create a table, and then find the new coordinates and graph the new one on there. Pause it and start it when you're ready. Okay, so I graphed the original in blue. I listed the coordinates here, A, B, C, D. Then I followed the rule, so I added 3 to each x coordinate and subtracted 1 from each y. And this prime notation, this means the A becomes A prime, a little dash after the letter, to indicate that that is the image. It's the same, kind of like a copy. When you take a copy machine, this is the new one. And copy machines are a little lighter. They don't always print it correctly. So it just kind of indicates the same one, but it's just a little different. So as we can see, it's moved, right 3, down 1, maintains shape and size. So now let's write a translation rule for this and verify that it is a translation, that it's an isometry. Isometry, remember, means same thing as rigid transformation, same thing as congruence transformation. Okay, so see if you can write the rule in coordinate notation and verify if it is indeed congruent. Pause it and resume when you're ready. Okay, notice triangle ABC. The image is triangle A prime, B prime, C prime. So we're going from blue to the red. So we're going left 1, 2, 3, 4 units and up 1. So from each point we should go left 4, 1, 2, 3, 4, and over 1, up 1. So our x coordinate is going left 4, so we subtract 4. Y coordinate goes up 1. So that's the rule. Verify that it's an isometry. Well, I find the length. So AC is 2 units straight up. A prime, C prime is 2 units. B prime to C prime is 3 units. BC is 3 units. So right triangle, so remember you can use Pythagorean theorem to find the hypotenuse, which since they both have the same legs, it'll be the same length. So 2 squared plus 3 squared. You see the math, we get that length is square root of 13. Since all the sides are the same length, it's congruent. All right, time for vector.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
All right, now that we know about vector, we can work through translating using the vector. So you can see the description of a vector, size and magnitude. So it tells us how far we are going in what direction. So in this case, this vector, FG, we have the initial point F, the terminal point or ending point G, tells us we're going 5 units right and 3 units up. So we use the component form of vector FG is 5, 3. So let's take a look at this vector over here, vector BC, because it starts at B, finishes at C. And its component will tell us how far we need, which direction we're going. So over 1, 2, 3, 4, 5, 6, 7, 8, 9 units, and down 2, so negative 2. And the next vector, since we start at S, is vector ST, similar to how we write array. And its component form, we go left 1, 2, 3, 4, 5, 6, 7, 8 units, so negative 8. And we don't go up or down, so it's negative 8, 0. Okay, and you can see an example below how we use the vector to translate the figure. You see the vertices of the original triangle ABC. And if we're translating using the vector 5, negative 1, that means we're going right 5 units and down 1 unit. So notice we just take all the coordinates, go right 5, down 1. And that maintains congruence in that figure. Okay? So that'll wrap up everything we need to know for translating. We've got some bonus material for those of you who are doing the accelerated geometry curriculum. We're going to learn about the matrix. So even if you're not in the accelerated group and you want to learn about the matrix, feel free to follow along and pay attention. Otherwise, you can stop the video and you'll do some practice problems on translations. All right, so using the matrix. First of all, we need to know what a matrix is and how it works. So we can use a matrix. Basically, it's just a set of all the x and y coordinates of all the points that we're looking at in one spot. So if we want to represent a point A, in coordinates, it would be negative 4, 0. So we write that as the matrix as listed down here. We put the x-coordinate on top, the y-coordinate below. The reason we do that is we can get a whole lot of information, a lot of coordinates all at once. So if we want the whole quadrilateral ABCD, as shown in the diagram on the right, our whole matrix shows all the x-coordinates and all the y-coordinates that correspond with each point, A, B, C, and D. So if I want to know the coordinate for D, it's 3, -1. And on the graph, over 3 down, -1. So that way we can list all the coordinates and we can do some calculations pretty quickly once we know what all the coordinates are. So just some information on how to add and subtract matrices and how that works. Basically, if we have two matrices, in the first case we have a 2 by 2 matrix, 2 rows and 2 columns. How we add and combine those is we add the top left numbers together. 5 and 1 is 6. The top right's -3 and 2 is -1. 6 and 3 in the bottom left is 9. And -6 and -4 is -10. So when you add or subtract matrices, you just look at whatever section in the matrix. They have to be the same size. So in this case, we have 3 columns and 2 rows, 2 by 3, and we just combine the same ones. So 6 minus 1 is 5. 8 minus -7 is 15. 5 minus 0, 5. And we keep the numbers in the same position. 4 minus 4, 0. 9 minus -2 is 11. -1 minus 3 is -4. Okay, so we need to learn the basics of how to add or subtract before we can talk about how we're going to use these to translate a figure. So let's take, for instance, the matrix 1, 1, 5, 0, 3, -1 represents triangle ABC. So we have a point at 1, 1, a point at 5, 0, and a point at 3, -1. Okay, so it's A, B, and C. And we want to translate using the matrix -1, 3. We can probably guess what we're doing to the x-coordinates and the y-coordinates. Since the x-coordinates are usually on top on the matrix, we're going -1 in the x-coordinates. So we're going left 1. And then we've got the 3's on the bottom. Each point goes 3 units. That's the y-coordinates. So we're going up 3. Negative would be going down. So because we are doing the same thing for each coordinate, we have the same numbers in each column. So we take our translation matrix, add it to the original polygon matrix, and when we combine those, we get our image matrix. And then we can graph those coordinates. So the matrix is used, when we want to translate a lot of points. So if you want to set up a computer program, setting up a matrix would be beneficial. But it's a way that we can combine a lot of points at once when we set up a program.